Hello everyone, this is the part 2 video of concept of sequence and series. Some concepts and some tests are discussed in the part 1 video. The remaining concepts will be discussed in the part 2 video. This is the part 2 video of sequence and series. Now let's move on to the concepts. First I explain some test. First test is comparison test. Suppose sigma an and sigma bn are series with positive terms. If sigma bn is convergent and an less than or equal to bn for all n, then sigma an is also convergent. Second condition is if sigma bn is divergent and an greater than or equal to bn for all n, then sigma an is also divergent. The first part says that if we have a series whose terms are smaller than those of a known convergent series, then this our series also convergent. The second part says that if we start with a series whose terms are larger than those of a known divergent series, then it is divergent. Okay, it is also divergent. This is the comparison test. Next, two results here. A p series sigma 1 by n power p converges if p greater than 1 and diverges if p less than or equal to 1. A geometric series sigma a r power n minus 1 converges if modulus r less than 1 and diverges if modulus r greater than or equal to 1. These two results are very useful when you are solving the problem by using comparison test. So these two are very useful notes. In using the comparison test, we must have some known series sigma bn. We must have some known series sigma bn for the purpose of comparison. Most of the time we use one of these two series, p series and geometric series. So these two series condition is very important for solving comparison test problems. Okay. Next, I explain one example. Determine whether the series sigma n equal to 1 to infinity 5 by 2 n square plus 4n plus 3 converges or diverges. You have to check the series is converges or diverges by using comparison test. For large n, the dominant term in the denominator is 2n square. So we compare the given series with the series sigma 5 by 2n square. This is the series sigma bn. Sigma 5 by 2n square. So clearly you can say that 5 by 2n square plus 4n plus 3 is less than 5 by 2n square. Clearly we can say that because the left hand side has a bigger denominator. So it is obvious. Okay. Obviously it is true. Next, analyze Bn. What is Bn? Sigma n equal to 1 to infinity 5 by 2n square. 2n square. So 5 by 2 is constant. Take it outside. I got sigma n equal to 1 to infinity 1 by n square. This is a p series. Sigma 1 by n power p is p series. Here p is 2. So it is a p series with p equal to 2. Here I use that condition p series converges if p greater than 1 and diverges if p less than or equal to 1. Here p is 2. This is greater than 1. So this series is convergent by using that result. Okay. So sigma bn. This is sigma bn. Sigma bn is convergent because p is greater than 1 and it is a p series. So it is convergent. Sigma bn is convergent and an is less than or equal to bn, the given series is an. An is less than or equal to bn, so sigma an is also convergent by using comparison test. Sigma bn is convergent and an is less than or equal to bn, so sigma an is convergent. So the given series is convergent by using comparison test. Next, limit comparison test. Suppose that sigma an and sigma bn are series with positive terms if limit n tends to infinity an by bn equal to c, where c is a finite number and greater than 0. That means c is greater than 0. Then either both series converges or both diverges. Okay, both series is converges or both diverges. It is a limit comparison test. Next, I will give one example. Test the series sigma n equal to 1 to infinity 2 power n minus 1 for convergence or divergence. Here I use limit comparison test. First, here we use the limit comparison test with an. The given series is an 1 by 2 power n minus 1. I select the bn, that is the dominant power in the denominator is 1 by 2 power n. 1 by 2 power n. This is the bn series. And first I obtain limit n tends to infinity an by bn. What is an? 1 by 2 power n minus 1. Here I write limit n tends to infinity also. Limit n tends to infinity 1 by 2 power n minus 1 divided by bn. So I write 2 power n. The next step is limit n tends to infinity 1 by 2 power n is take it outside. I got 1 minus 1 by 2 power n. 2 power n. Here 2 power n cancel. Finally, I got limit n tends to infinity 1 by 2 power n is 0. So 1 by 1, 1. This is limit exists and this value is greater than 0. Greater than 0. So these two series are converges or both diverges. Both converges or both diverges. So first I check Bn. Here Bn is sigma Bn equal to sigma 1 by 2 power n. This is the series. It is a geometric series with r equal to, it is geometric series with r equal to 1 by 2. The note, using that note, the geometric series converges if modulus r is less than 1 and diverges if modulus r is greater than or equal to 1. Here r is 1 by 2, so modulus r equal to 1 by 2 is less than 1. So this series sigma bn is convergent because modulus r is, it is a geometric series and modulus r is less than 1. So sigma bn is convergent. So by using limit and limit n tends to infinity an by bn also greater than 0. So by using limit comparison test sigma an is also convergent. Sigma an is the given series. The given series also convergent. This is the one example of limit comparison test. Limit comparison. The next definition is absolute convergence. A series sigma an is called absolutely convergent if the series of absolute values, that means sigma modulus an is convergent, then it is said to be sigma an is absolutely convergent. Next, results, some results here. A series sigma an is called conditionally convergent. That means if it is convergent but not absolutely convergent. The second result says if a series sigma an is absolutely convergent, then it is convergent. That so the result gives absolutely convergent gives convergent, but convergent does not gives absolutely convergent. It is the results. Next, ratio test. Next, I explain ratio test. The ratio test, first one is if limit n tends to infinity modulus of an plus 1 by an equal to L, that limit value is capital L, it is less than 1, then the series is sigma n equal to 1 to infinity an is absolutely convergent. Absolutely convergent means it is also convergent by using that result, okay, and therefore convergent also. Second part, if limit n tends to infinity modulus an plus 1 by an equal to L is greater than 1, or the limit n tends to infinity modulus an plus 1 by an equal to infinity, then the series is divergent. Suppose you got limit n tends to infinity an plus 1 by modulus an plus 1 by an equal to 1, the ratio test is inconclusive. Inconclusive means there is no information, that is no conclusion can be drawn about the convergence or divergence of sigma an, the given series sigma an. Okay, this is the ratio test. Next, I will give example of ratio test. Here one example, test the series sigma n equal to 1 to infinity minus 1 whole power n cube by 3 power n for absolute conversion only. Here we use ratio test with an. What is the an value? Minus 1 whole power n cube by 3 power n. So I write here an plus 1 also. An plus 1 is minus 1 whole power n plus 1, n plus 1 whole cube divided by 3 power n plus 1. This is the an plus 1 the term. Next, I find modulus of a plus an plus 1 by an equal to minus 1 whole power n plus 1 n plus 1 whole cube divided by 3 power n plus 1. Next, divided by an. So, I write the multiplication as minus 1 whole power n. Sorry, it is denominator. 3 power n by n cube into minus 1 whole power n. Here, minus 1 whole power n minus is available, but this is modulus. So, I write plus 1, plus term only, modulus of minus 1 is plus 1, n plus 1 whole cube. In this term, I take it outside n, so I got n cube. So 1 by 1 plus n whole cube divided by, I write 3 power n plus 1 becomes 3 power n into 3. So 3 power n into n cube. Next n cube cancel, 3 power n cancel. The next step, limit n tends to infinity. This is an plus 1 by an modulus. This is equal to limit n tends to infinity 1 by n is 0. So 1 plus 0 1 cube is 1. The denominator is 1, sorry, numerator is 1, and the 3 power n cancel, n cube cancel. And the denominator is 3. So finally I got limit value of limit at tends to, as n tends to infinity, modulus an plus 1 by an is 1 by 3. This is less than 1. So by using the ratio test, the limit is less than 1, then the series is absolutely convergent. Absolutely convergent means it is also convergent. So by using the ratio test, the given series is convergent. Convergent and absolutely convergent. So this is one example. Next, another one example. Test the convergence of the series sigma n equal to 1 to infinity n power n by n factorial. Here we use ratio test with an equal to n power n by n factorial, an plus 1 equal to n plus 1 whole power n plus 1 by n plus 1 factorial. Next, I find the what's the values. Here all the terms are positive, so we don't need to absolute value sign, modulus value. We don't need to modulus sign. Okay, an plus 1 by an equal to n plus 1 whole power n plus 1 by n plus 1 factorial into n factorial by n power n. I write this term, take it n outside, I got n power n into 1 plus 1 by n whole power n plus 1. Okay, next term is n plus 1 factorial. N plus 1 factorial, I write n plus 1 factorial is n plus 1 into n factorial, and this is n factorial by n power n. So next, here n power n plus 1 is available, n power n plus 1. So this is wrong. I write this one as this type, n plus 1 into n plus 1 whole power n. N plus 1 whole power. I write n plus 1 whole power n plus 1 is n plus 1 into n plus 1 whole power n. And then write n plus 1 whole power n is 1 plus 1 by n whole power n and n power n. So finally I got the numerator is this term, n plus 1 into n power n into 1 plus 1 by n whole power n. Here I cancel all the terms, n power n, n power n, n factorial, n plus 1, n plus 1. Finally I got 1 plus 1 by n whole power n. So limit n tends to infinity, an plus 1 by an equal to limit n tends to infinity 1 plus 1 by n whole power n. This is the known result, limit n tends to infinity 1 plus 1 by n whole power n value equal to e. This is 2 point something. So this value is greater than 1. By using the by using the limit comparison test. What is that? Sorry, ratio test. By using the ratio test, this value is greater than 1. Greater than 1, then it is divergent. Okay, so the given series is divergent. This is the one example of ratio test. Divergent because the limit value is greater than 1. So it is divergent. Next, root test. The first condition is if limit n tends to infinity, nth root of modulus an equal to L, it is less than 1, then the series is absolutely convergent. Absolutely convergent gives the convergent also, and therefore convergent. Okay. 2. Second condition is if limit n tends to infinity, nth root of modulus an equal to L, it is greater than 1 or this value is infinity, does not exist, then the series is divergent. Third condition is if limit n tends to infinity, nth root of modulus an equal to 1, the root test is inconclusive. That means there is no information. Suppose you got the value equal to 1. In this case, you cannot use the root test. Okay. So this is the root test. Next, I will give one example. Test the convergence of the series sigma n equal to 1 to infinity 2n plus 3 by 3n plus 2 whole power n. So an, here the an is nth term is 2n plus 3 by 3n plus 2 whole power n. First I take the nth root of modulus an. That means this is nth root of modulus an is 2n plus 3 by 3n plus 2 whole power n 1 by n. Finally, I got 2n plus 3 by 3n plus 2. I can write, take it n outside, 2 plus 3 by n, and denominator take it n outside, I got 3 plus 2 by n. So finally I got n cancel this value. Next, limit n tends to infinity, nth root of modulus an equal to n cancel and limit n tends to 3 infinity 3 by n is 0 and this term also 0 1 by n 1 by n. Okay, limit n tends to infinity 1 by n is 0, so this term 0. Finally I got the numerator is 2 and denominator is 3. This is 2 by 3. This is less than 1. So by using the root test, this value is less than 1. So the given series is absolutely convergent. That means it is convergence by using the root test. So the given series is absolutely convergent and convergent also. Convergent. This is the one example of root test. Next, the above convergence test that we have apply only to series with positive terms. The above 4 convergent test, I explained 4 test: integral test, comparison test, ratio test, 2 test. The above convergent test that we have apply only to series with positive terms. Next, we learn how to deal with series whose terms are not necessarily positive. That means whose terms are alternatively in sign, plus and minus. This series is called alternating series. Okay. Next we have to learn how to deal the alternating series. What is alternating series? An alternating series is a series whose terms are alternatively positive and negative. Then it is called alternating series. Okay. Next I will give 2 example. Okay, that is, suppose this is one series 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5. This is one example of alternating series. How to write this one? Plus minus etc. This is one. How to write this one? Sigma n equal to 1 to infinity minus 1 whole power n minus 1, then 1 by n. Here the terms are alternatively positive and negative. So it is called alternating series. It is the one example. Similarly, we can write the next example is minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 4 by 5. Sorry, minus 1 by 2, 2 by 3, 2 by 3, 3 by 4, 4 by 5 minus etc. This is equal to sigma n equal to 1 to infinity minus 1 whole power n. Here n plus n minus 1 or n plus 1 is okay. Okay. Here minus 1 whole power n, because the starting term is negative. So minus 1 whole power 1 is minus. Okay. Minus 1 whole power n by n plus 1. This is the another one example of alternating series. What is mean by alternating series? Alternating series is a series whose terms are alternatively positive and negative. Next, I explain alternating series test. If the alternating series, the given series is alternating series, sigma n equal to 1 to infinity minus 1 whole power n minus 1 or n plus 1, bn equal to b1 minus b2 plus b3 minus b4 and etc. and bn greater than 0, satisfies first condition is bn minus 1 is less than or equal to bn for all n. Bn minus 1 is less than or equal to bn for all n. And second condition is limit n tends to infinity bn equal to 0, then the series is convergent. It is the alternating series test. It is also called Leibniz test. Alternating series test is also called Leibniz test. Okay, next I will give the one example. Yeah, test the convergence of series 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 is what? You have to check the series is convergent or not. So the given series is, I can write sigma n equal to 1 to infinity minus 1 whole power n minus 1 1 by n. This is the given series. First, you have to check the first condition. What is the first condition? Bn plus 1 is, or sorry, n minus 1. N minus 1 is always less than or equal to Bn. Bn minus 1 or n plus 1? No, n plus 1. Here Bn plus 1 is always less than or equal to Bn. Okay. So Bn plus 1 is less than or equal to Bn. It is less than. Obviously, because 1 by n plus 1 is 1 by n. It is true because 1 by n plus 1 is 1 less than 1 by n. Denominator is here highest value. So it is less value. 1 by n plus 1 is less than 1 by n. It is true. So the condition 1 is satisfied. What is the condition 2? Limit n tends to infinity bn equal to. So limit n tends to infinity. Here bn is 1 by n. 1 by n, limit n tends to infinity 1 by n equal to 0. So limit n tends to infinity bn equal to 0. The condition 2 also satisfied those. So the given series is convergent. The given series is convergent. Here I changed the sign. Here Bn plus 1 is less than or equal to Bn. This is the first condition. Okay, Bn plus 1 is less than or equal to Bn. So this is the alternating series test. This is the one example of alternating series test. Next, another example. Test the series sigma n equal to 1 to infinity minus 1 whole power n 3n by 4n minus 1. The given series is alternating series because the terms are alternate in sign, plus minus plus minus plus minus plus etc. Here first I check the second condition. Limit n tends to infinity bn equal to limit n tends to infinity bn is 3n by 4n minus 1. This is equal to limit n tends to infinity 3n by 4n is, take it outside. I got 1 minus 1 by 4n. This value is limit n tends to infinity 1 by n is 0. So this value is 0. 1 minus 0 is 1. N cancel. Finally I got 3 by 4. This is not equal to 0. Here condition 2 is not satisfied in alternating series test. So in this case we cannot use the alternating series test. Now we look at the limit of the nth term of the series. Nth term of the series, not Bn, nth term of the series. So limit n tends to infinity, nth term is called an. Okay, limit n tends to infinity. What is the nth term? Minus 1 whole power n, 3n by 4n minus 1. This is the nth term limit. Okay, we look at the limit of the nth term of the series. This limit does not exist. This limit does not exist. That means it is infinity. This limit is does not exist. So the series is diverges. How can I say the series is diverges? By using the test for divergence. Test for divergence. So the series is diverges by using test for divergence. Test for divergence. Okay, divergence. So finally I got the given series is diverges. This is the two example of how to use the alternating series test. This is the two example. Next, strategy for testing series. Now I explain what kind of test should be used for any series. What kind of test should be used for any series. First, comparison test. If the series has a form that is similar to a P series or a geometric series, then one of the comparison tests should be considered. That means comparison test or limit comparison test. In particularly, if an is a rational function, an is a rational function or an algebraic function of n, then the series should be compared with the P series. So if the series has a form of that is similar to P series or geometric series, then you can use comparison test or comparison limit comparison test. Next, test for divergence. If you can see at a glance that limit n tends to infinity an not equal to 0, then the test for divergence should be used. Next, integral test. If an equal to f of n, an equal to f of n, here integral 1 to infinity f of x dx is easily evaluated, then the integral test is effective. Next, ratio test. Series that involves factorials or other products, including a constant raised to the nth power, then you can use the ratio test. Series that involve factorials or other products, including a constant raised to the nth power, then you can use ratio test. Next, root test. If an is the form bn whole power n, then the root test may be useful. An is the form bn whole power n. Last one is alternating series test. Here, if the series is of the form sigma minus 1 whole power n bn or sigma minus 1 whole power n minus 1 n plus 1 bn, then the alternating series test is an obviously possibility. Okay. The positive negative terms sign changes positive to negative. So alternative terms are sign changes positive negative, then you can use alternating series test. This is the what kind of test should be used for any series explanation. Okay, strategy for testing series. Next is power series. Power series. A series is of the form sigma n equal to 0 to infinity Cn x minus a whole power n equal to C0 plus C1 x minus a plus C2 into x minus a whole square plus C3 into x minus a whole cube is called a power series x minus a or a power series about a. It is called a power series. Next, I will give an example. For what values of x does the series sigma n equal to 1 to infinity x minus 3 whole power n by n converge? For what values of x does the series is converge? Okay, let here an equal to x minus 3 whole power n by n. This is the nth term. An plus 1 is x minus 3 whole power n plus 1 divided by n plus 1. In this problem, I use ratio test. So, I find first modulus of an plus 1 by an. I already explained what is ratio test, etc. So, an plus 1 is x minus 3 whole power n plus 1 divided by n plus 1 divided by an is n by x minus 3 whole power n. I can write this one is x minus 3 whole power n into x minus 3 whole power 1. So x minus 3 whole power n cancel. Next, in this case, I take it n outside, I got 1 plus 1 by n. So finally, I got in the numerator x minus 3 divided by in the denominator 1 plus 1 by n modulus of. Limit n tends to infinity modulus of an by n plus 1, an plus 1 by an equal to limit n tends to this value is limit n tends to infinity 1 by n is 0. So finally I got modulus x minus 3. Modulus x minus 3. By the ratio test, the given series is absolutely convergent and therefore convergent also when modulus of x minus 3 less than 1. Convergent when modulus x minus 3 less than 1. So this gives modulus x minus 3 less than 1 means minus 1 less than x minus 3 less than 1. That means minus 2 less than, sorry, plus 2, minus 3, minus 1 plus 3. So plus 2 less than x less than 4. So the series is convergent when 2 less than x less than 4. Next condition is divergent. Okay. The series is divergent when, by using ratio test, the series is divergent when modulus x minus 3 greater than 1. That means it gives x minus 3 greater than 1 means x less than 2, x less than 2 and x greater than 4. X less than 2 or x greater than 4. The series is divergent. What values? X less than 2 or x greater than 4. The ratio test gives no information. No information when modulus x minus 3 equal to 1. Modulus x minus 3 equal to 1. Then what values of x satisfies this equation? Modulus x minus 3 equal to 1, x equal to 2 and x equal to 4. X equal to 2 and x equal to 4. So we must consider x equal to 2 and x equal to 4 separately. So first, if you put x equal to 4 in that series, given series, put x equal to 4 in the given series, I got sigma x equal to 4 means 4 minus 3, 1, 1 power n is 1, 1 by n. Sigma n equal to 1 to infinity, 1 by n. It becomes the harmonic series or the nth series with p equal to 1. The harmonic series is which is divergent. So the harmonic series is always divergent. So which is divergent when divergent. When divergent when x equal to 4. And next one is x equal to 2 condition. If you put x equal to 2 in the original series, given series, I got 2 minus 3 whole power n, that is minus 1 whole power n. So the given series become minus 1 whole power n, 1 by n. Which by using the alternating series test, the given series is the series sigma minus 1 whole power n 1 by n is converges. Okay, by using alternating series test. Okay, so the given power series converges for 2 less than or equal to x less than 4 only. The given power series converges only for 2 less than or equal to x less than 4. 2 less than x less than 4 condition is here. Converges x equal to 2 also. So 2 less than or equal to x less than 4 in x equal to 4, which is divergent. So here not equal is not available. So converges only when 2 less than or equal to x less than 4. This is the one example of power series. Next, I explain some important series. Taylor series. Taylor series is of the form f of x equal to sigma n equal to 0 to infinity f nth derivative of a by n factorial into x minus a whole power n. Expand this f of a. First put n equal to 0, I got f of a, plus put n equal to 1, I got f dash of a by 1 factorial x minus a. Similarly, f double dash of a. This is not f double dash of a, f triple dash of a. F double dash of a by 2 factorial x minus a whole square plus f triple dash of a by 3 factorial x minus a whole cube plus etc. This is called the Taylor series. Next, Maclaurin series. F of x equal to sigma n equal to 0 to infinity f nth derivative of 0 by n factorial x power n. This is equal to f of 0 plus f dash of 0 by 1 factorial into x plus f double dash of 0 second derivative, double dash of 0 divided by 2 factorial into x square. Next one is f triple dash of 0 divided by 3 factorial into x cube plus etc. This is the Maclaurin series. These are the some basic and important concepts and results in the sequence and series topic. In the forthcoming videos, let me solve previous year GATE questions related to this topic for all branches. If you have any doubt in this topic, then you can ask in the comment section. Let me try to clarify your doubts. Thank you. See you in the next video. If you like this video, please like, share and subscribe my channel to encourage me. Thank you.